In the name of Allah, hello everyone. Today I am excited to present a technical review on the paper Simple and Effective Frequency-Aware Image Restoration for Industrial Visual Anomaly Detection. My name is Ali Ruhbakhsh and I have been working on the practical implementation of this method within the scope of our mechatronics course. Let's dive straight into the challenge of industrial anomaly detection. From now on, I call frequency aware image restoration FAIR. Okay. The industrial inspection. We face a paradox. We need to detect defects, yet we rarely have enough defective samples to train a robust model. Most production lines are clean, so our training data consists almost exclusively of normal images. When we do get a defect, like a scratch, a crack, or a stain, it's often very subtle. The challenge is, how do we build a model that understands what normal looks like well enough to flag anything else as an anomaly? The standard approach is image reconstruction. We use an autoencoder or a unit to reconstruct the input. But there's a trap. A powerful network can become too good. It might learn to reconstruct even the defects, which effectively hides them from our detection map. Our, our objective with fair frequency-aware image restoration is to break this identity mapping. We want to force the network to focus on structural integrity rather than just pixel values. And in the output, we cannot detect the defect. Frequency-aware reconstruction fair attenuates low-frequency components. The network learns edges, textures, and normal structures. The defect becomes more visible in the output. Conventional reconstruction, a powerful autoencoder or unit may approach identity mapping. The defective region is also reconstructed. Its reconstruction error becomes small. This is where the frequency domain comes in. Think of an image as a collection of frequencies. The low frequencies are the smooth background and lighting, the boring stuff. The high frequencies contain the edges, the fine textures, and crucially, the anomalies. By applying a Butterworth high-pass filter before the data hits the unit, we effectively force the network to ignore the background noise and pay attention to those fine, sharp edges where a defect would exist. We are guiding the network's attention. Input image prepared for processing. With Fourier transform, we move it from the spatial domain to frequency components and apply a Butterworth high-pass filter. And after that, the unit can detect the defect. Our architecture is built on a unit. As you see here, we are using the Butterworth filter to pre-process the input. The encoder uses skip connections to preserve high-resolution spatial details, while the decoder tries to reconstruct the image based only on the filtered high-frequency information. Finally, we compute the anomaly map by looking at the pixel-wise difference. If the network fails to reconstruct a specific texture, the difference pops up as our anomaly. So before UNet, we have a frequency filter, frequency domain input with Butterworth's high-pass filter, and after that we have encoder skip connections, multi-scale features, decoder, and output. Let's look at the implementation workflow. We resize our images and apply data augmentation. The magic happens in the middle. We apply the fast Fourier transform FFT, filter out the low frequency noise, and pass that edge focused data into our UNet. We train using backpropagation to minimize the reconstruction loss. Once the model is trained, inference is straightforward. Compute the reconstruction error, aggregate it, and generate our AUROC scores. So first of all, the preparation, resize images, apply data augmentation, and prepare normal test images. The second step, it's about frequency processing, apply fast Fourier transform, then the Butterworth high-pass filter, and the next step is reconstruction, feed input into UNet, calculate loss, backpropagate and save model weights, and after that it is detection step. Compare inputs and output to generate the anomaly map. And the last step is evaluation. Aggregate the map and calculate image AUROC, pixel AUROC, and Pro. I performed the initial implementation on Google Colab using the NVTech 80 dataset. Especially, I focused on the butter class, and we used a batch size of 4 running for 800 initial epochs. It was a rigorous training session, taking roughly 12 hours. The smoke test passed successfully, which gave us the green light to proceed with the full evaluation, and the full evaluation passed successfully with the NVTech 80 dataset, 4 batch size, and 800 initial epochs. Now let's look at the numbers. It is critical to compare our practical execution against the paper's baseline. As shown in this table, the paper reports an image AUC of 100% and a pixel AUC of 98.4%. For the butter class, my implementation yielded an image AUC of 100% and a pixel AUC of 98.28%. These results are extremely close, confirming that the FAIR method is both effective and reproducible. And as you see, the results of the NVTech 80 dataset of FAIR with different synthesized anomalies: carpet, grid, leather, tile, wood, bottle, cable, capsule, hazelnut, metal nut, peel, screw, toothbrush, transistor, and zipper. The average score, as you see, for D synthesize anomaly about diversity is 98.5, 97.3, and 93.6. About another synthesized anomaly, 98.6, 98.2, and 94. And about the last synthesized anomaly, 99.1, 98.3, and 95. To conclude, FIR is a simple yet powerful modification. By suppressing low-frequency components, we prevent the network from cheating by blindly copying inputs. Instead, we force it to learn the structural rules of the product. The practical execution on the butter class was a success. The next logical step is to scale this across all classes in the NVTech dataset to confirm generalizability. Thank you for your time, and I'm happy to answer any questions.